Hello everybody. Since we have seen how to define and write down functionals, and in particular also functionals of the density, we now would like to understand how to manipulate them. The most important thing to do then is to understand how to perform functional derivatives. And this is the aim of this module. So we start with a generic function and decide to construct a functional of this function. It can be a simple function, like here a local multiplicative functional, or something more complicated, like a functional that depends in a certain way not only on f, but also on its derivatives, for instance. And now, what we want to describe is how a functional changes when the function itself changes. So, let's imagine a small variation of the function, here described by epsilon times eta. And we ask, how much the final value of the functional changes when we consider small changes in epsilon? Of course, you might recognize here the analogy with the concept of derivative. And in fact, using the analogy with the derivative of a function, I would like to guide you to the concept of functional derivative. Here you see the crucial step is to consider the incremental, that is the difference between the function evaluated at some incremented minus the function at that point. Let's do the same with the functional. We have to construct the functional at a varied function, which is here just f, plus epsilon eta. Eta is a generic function, sometimes it is called the test function, and epsilon is the infinitesimal, the small quantity. The important thing to notice here is the following. If you consider all this in terms of epsilon, this is a simple function. Once you consider a fixed x, and so a fixed f and eta, everything will just depend on epsilon like a simple function, which can be Taylor expanded. Let's do it. When we expand, we have the first trivial term, then we have the first derivative of f with respect to epsilon. It is a total derivative, because capital F here behaves as a simple function of epsilon. Then we have the second derivative with respect to epsilon, and so on. We can then construct, in analogy with the derivative of a simple function, the incremental ratio, which will be, by definition, related to the first derivative with respect to epsilon. So, we are ready to define the functional derivative. As it follows. If the first derivative of capital F with respect to epsilon exists and can be written as the following integral in the x of something times the eta function, then this something is defined as the functional derivative with respect to function f. And for the same reasons, if the second derivative here in the Taylor expansion in epsilon can be written as a double integral in x and x prime, well, the integrand is the second functional derivative. And of course, we could go on in the Taylor expansion in epsilon and define the generic nth functional derivative associated with the nth term in the Taylor expansion. Now, I know what you're thinking. There's something that might be bothering you in the definition. Why the definition in the functional derivative is done in this weird way, inside the integral? Well, let's have a look again at the definition of the derivative of a simple function. It is simply given by the ratio of the incremental difference and epsilon. So, why we do not simply define the incremental ratio here as the functional derivative, instead of going through the definition inside the integral? Well, the reason is very simple. Because we have the testing function here, eta of x, we want to define the functional derivative independently of the testing function. We want this to be the functional derivative for any possible eta. And in fact, you would immediately recover the most intuitive definition if you choose as testing function a delta function. In this case, and without loss of generality, the functional derivative is indeed just the incremental ratio, exactly like a simple derivative of a function. But the important point here is that the functional derivative can be defined for any testing function eta. Okay? And let me give you another point of view that shows that this way of writing can also be very intuitive. Let's suppose we have a function of many variables, okay? Not just 2 or 3, really many variables. If we want to write the generic variation of capital F, we have to consider the variation of f with respect to all its variables, which implies the partial derivative with respect to f1, f2, all variables. Now, and here is the trick. Imagine that you have so many variables in your function that instead of labeling them with discrete i's, 1, 2, 3, and so on, you use a continuous variable x, because there are so many. The sum becomes an integral, and your little infinitesimal variation delta fx can always be written like a function times an infinitesimal, so to recover the definition of the functional derivative. A functional derivative can also be seen as a generic variation of a function which has many variables. Sometimes this is the first point of view that is given in textbooks. Okay, it's time to become operative and see in practice how this definition of the functional derivative works. I will show you 2 examples. The first one is about this very simple functional, the value of a function at a certain x0. What is the functional derivative of this functional? Let's apply the definition. We Taylor expand the functional where the argument has been incremented and have a look at the first derivative. Because remember, the first derivative in epsilon is related to the first functional derivative. Let's take the derivative with respect to epsilon and now ask the question, can the derivative be written as an integral of something times the testing function? Yes, indeed. Here it is. So the functional derivative of this functional is simply the delta function. And from this, you can immediately work out the generalization for this whole class of functionals, which in our density functional approach means that we are able to solve the functional derivative for this term of the energy, right? I let you work it out. But now, let me give you a second, more complicated example, the case of a functional in which the dependence is not only on f, but also on the first derivative of f. If you think this is a weird class of functionals, let me show immediately an example. The classical Lagrangian action, functional of the generalized coordinates q, but the Lagrangian depends on t, q of t, and q prime of t independently. Or, to stay in our density functional word, the von Weizsäcker kinetic energy term that depends on the density and the gradient of the density. So, how to do the functional derivative in this case? Well, we apply the definition. Remember, we Taylor expanded the functional of the incremented function as if it were a simple function of epsilon. And we look at the first derivative. Here, you might notice that the increment is done both on the function and on the first derivative f prime. We can expand the function g that contains the trivial non-varied value, the partial derivative with respect to f, and the partial derivative with respect to f prime. The function g is, after all, a function of 3 variables. If we carry out the derivative with respect to epsilon, only 2 terms survive. And now you see one thing. We have an integral in the x of eta prime, which means first derivative with respect to x. So we can integrate this term by parts and have the following. What is the advantage? That we can put the integrated term to 0, because we can always choose a testing function that is 0 in a and b, without loss of generality. Essentially, what we are doing is to consider a varied function everywhere except in the endpoints. And that's why this approach is sometimes called fixed endpoints approach, and is completely general. So we now have our first derivative term in the Taylor expansion, and again, we have to see if this can be written as an integral of something times eta. And since this is indeed the case, we reached the final result. The functional derivative of this class of functionals is this very appealing formula here. We end this video here. We now have the necessary ingredients, the functional concept, how to perform functional derivative, to tackle density functional theory. Of course, you will need a bit of a practice with this. So do not miss the lecture notes and don't forget to do the exercises, where you will be able to confront yourself to other examples and situations, crucial to really do DFT. Goodbye.